Hi and Assalamualaikum. We are from Group CS 2416C and we're going to present about the P chart and exponentially weighted moving average UMA on the paper production data set. I am Nur Aini Shazana and my other group members are Yasmin Kamilia, Nur Farida, Rabiatul Adawiyah and Siti Nabila Shahira. So first, what is P chart and UMA? P charts are control charts that are used to monitor the proportion of defective items in a sample over time. They provide valuable insights into process stability. Points that fall outside the limits indicate that the process may be out of statistical control and warrant further investigation. It is effective in identifying process variations, simple to construct and interpret, and versatile in applications. Then, what is UMA? UMA is a statistical technique used to track and predict the future behavior of a process based on past data. UMA charts use a smoothing parameter lambda to determine how much weight is given to recent observations versus historical data. Smaller values prioritize stability, while larger values increase responsiveness to recent changes. UMA charts can effectively filter out random noise in the data, providing a clearer picture of the underlying process trend. Both of these charts can be validated by using process capability indices like CP, which measure the ability of the process to produce within specifications, or actual capability indices like CPK, which assess the chart sensitivity to detecting changes.
So next, we're going to move to the methodology description of data. This data is about the paper production for 25 days. This data consists of 5 variables, which are x1, x2, x3, x4, and x5.
To analyze the data by using P chart, here is the steps to construct the P chart. First, calculate the proportion defective for each sample, which is P hat equals to number of defective divided by the number of sample size. Second, calculate the average of proportion of defective, which is P bar equals to summation of P hat divided by the number of sample subgroup. Third, calculate the control limits, which is upper control limit UCL equals to P bar plus 3 square root P bar multiplied with 1 minus P bar over N. While the center line we can get from the average proportion of defective. Then for the lower control limit LCL, which is P bar minus 3 square root P bar multiplied with 1 minus P bar over N. Next, step 4 is plot the graph of proportion non-conforming, which is P chart. The last step is interpret the results from P chart. When all points fall between the UCL and LCL, the process appears to be in control. But if any points that exceeds this range will indicate an out of control situation, which leads to further investigation. Note that if LCL value is negative, set it to 0 because proportion of defective cannot be a negative value.
Next, we're going to have a look at the UMA. For step 1, we need to set the initial parameter. Lambda is the smoothing constant. Nu null is the process target or the initial mean of the data. L is the control limit multiplier. Sigma is the process target or the initial mean of the data. For step 2, we need to compute the UMA statistic. The UMA statistic Zi at time I is calculated using the formula Zi equals to lambda xi plus 1 minus lambda in bracket Zi minus 1, where xi is the observed value at time I and Zi minus 1 is the UMA statistic from the previous time step. Step 4, we need to determine control limits. UCL equals to nu null plus L sigma square root of lambda over 2 minus lambda 1 minus 1 minus lambda to the power of 2i. LCL equals to nu null minus L sigma square root of lambda over 2 minus lambda 1 minus 1 minus lambda to the power of 2i. Step 5, plot the UMA chart. Plot Zi over time along with the UCL and LCL. Investigate if Zi stay within the control limit. Process Capability Analysis, CP and CPK. The first step of calculating CP and CPK is determine the specification limit. USL is the maximum allowable value for the process output, while LSL is the minimum allowable value for the process output. Step 2. Calculate the process mean. Nu equals to summation of xi over m, where xi is each individual data point, m is the total number of data points. Step 3. Calculate the process standard deviation. Sigma equals to R bar over D2. R bar is the average range of subgroups, and D2 is a constant based on the subgroup. Step 4. Calculate the CP. CP equals to USL minus LSL over sigma. Step 5. Calculate the CPK. CPK equals to minimum of USL minus nu over 3 sigma, comma nu minus LSL over 3 sigma. The CPK value is the minimum of the two values. The first one measure the capability relative to the upper specification limit, while the second one measure the capability relative to the lower specification limit. Next, step 6. Interpret the CPK value. A CPK value greater than 1 or equal to 1 indicates the process can produce product within the specification limit. A CPK value of 1 means the process is at the edge of capability, while value less than 1 indicates that the process is not capable of consistently producing product within the specification limit. Step 6. Interpret the CPK value. A CPK value greater than 1 or equal to 1 indicates the process can produce product within the specification limit. A CPK value of 1 means the process is at the edge of capability, while value less than 1 indicates that the process is not capable of consistently producing product within the specification limit.
Next, for result and discussion, for p-chart calculation, the sample size n equal to 5, sample subgroup m equal to 25, the specification limit USL equal to 5,200 and LSL 4,800. So, based on the table, the defective column will calculate based on specification limit, where it was decided based on number of samples that out of the specification limit. Next, for p hat column, it was the proportion of defective for each subgroup. Next, for p-chart calculation, we calculate center line, which is p bar, that equals to 10.8 over 25 equals to 0.432. And then for upper control limit UCL equal to 0.432 plus 3 square root of 0.432, 1 minus 0.432 over 5, and we get 1.096588. And then for lower control limit LCL, 0.432 minus 3 square root of 0.432, 1 minus 0.432 over 5, and we get negative 0.23259, approximately equal to 0. Next, this is the graph that we get from the value that we calculate before, and then it shows that the process is in control, where no points over upper control limit and lower control limit. And then it also no sensitive patterns based on sensitizing rules for show height control chart.
Now we move to the UMA calculation, where target mean mu null is equals to 5074.064. For the process standard deviation sigma, by using the formula R bar divided by D2 equals to 219.9828. So for the control chart parameter L, we choose 2. the smoothing parameter lambda equals to 0.2. So now we need to find the value of UMA statistic at time I for each 25 sample subgroups. So for the Z1 equals to 507.1312. For the second UMA statistic at time equals to 5091.3050. Repeated the process again until 25, and the last value for the Z25 we got
charts
508.6569.
in monitoring the stability of a paper production
After
process.
we got the value
The
for
feature analysis
UMA
indicate that
statistic
the
at
production
time I
process
for
remain within
25
control
sample
limits throughout the
subgroups.
monitoring
So we need
period,
to calculate
with
the
no
upper
points
and the
exceeding
lower
the
control limit
upper or
for
lower
each of
control
the
limits.
sample.
The UMA charts also
So
confirm
for the
the
target mean,
stability of the
process
process,
standard deviation,
with the
control
weighted
chart
average
parameter
staying
and
within the
smoothing
control
parameter,
limits.
we use
However,
as
the
in the
analysis
previous
revealed
slide
periods of
of the
concern,
value.
particularly between days 12 and 15,
Then
where
we
production
need
values
to
approach the lower control limits,
calculate
signaling the
for
need
the
for
first
closer monitoring.
UCL.
By
We got
leveraging the findings, manufacturers can proactively address process
512.0571.
variability,
For the second
minimize
UCL, we
defects, and
got
maintain product quality.
5186.7502,
That's all from
and
us.
repeated
Thank
the
you.
process again until 25, and the last value for UCL is 5220.7182. Now we calculate for the lower control limit. For the first one is 4786.0709. For the second LCL, we got 4961.3778, and repeated the process again until we get for the sample 25, which is 4927.4098 as in the previous as in the slide. Now we move to the UMA chart as shown in the slide. So the process is in control, no points over upper control limit and lower control limit line. Unfortunately, warning signals during day of 11 to 14 when production almost approaches LCL, and need to monitoring and investigating those periods for the stability in the future. For process capability analysis, we start with process capability, which is CP, where process mean X bar equal to 5074.064, standard deviation sigma equal to 219.9828, and we calculate CP by using the formula before, and we get 0.3031, where the value of CP is lower than 1, and process uses up more than 100% of tolerance band, where large number of non-conforming will be produced. Next, process capability index, which is CPK, based on the previous value of process mean and process standard deviation, we use that value to calculate CPK, and then we get CPK equals to minimum 0.1908. Since CP equal to 0.3031 greater than CPK equal to 0.1908, therefore process is off-center.
For the conclusion, this study aimed to evaluate the effectiveness of P charts and UMA control charts in monitoring the stability of a paper production process. The P chart analysis indicate that the production process remain within control limits throughout the monitoring period, with no points exceeding the upper or lower control limits. The UMA charts also confirm the stability of the process, with the weighted average staying within the control limits. However, the analysis revealed periods of concern, particularly between days 12 and 15, where production values approach the lower control limit, signaling the need for closer monitoring. By leveraging the findings, manufacturers can proactively address process variability, minimize defects, and maintain product quality. That's all from us. Thank you.